Good afternoon, everyone. Give me a minute. Yep. So, so today we are going to cover the fundamental. Pardon my voice, please. I know there is a distortion because of the viral and all. So I'm trying. I'm on medications and all. So pardon me for that. But today, what we aim for is to understand basics of the complexity classes, which is a very fundamental thing for us to understand that why we need quantum computing, like not the technology, not the algorithm, but directly the computing part. So for that, we will be today understanding a little about automata theory, or we will consider a problem. We'll try to understand that why it's a very NP hard problem, or why it's kind of a certain thing that we need to consider separately, which we cannot do traditionally. Along with that, we will also be considering that what is P, what is NP, what is NP complete and NP hard. So this is fundamentally what we aim for today's class. So today's class was a little unplanned, but I hope you enjoy, and like this class also remains as like kind of engaging as it was earlier as well. So I expect that kind of engagement from you as well. So on that note, let me start. Let me hide it. Just a minute. Yeah. So we all know basic things like quantum is literally it's something for the very complex problems. It's built up for very complex problems. But how do we define this kind of complexity? Let me consider a basic problem known as PSP, or the traveling salesman problem. If you remember, in lecture 1, we talked about this problem that it actually creates an exponentially kind of an explosive search space. Okay, so that kind of a problem we are referring here, which is called the traveling salesman problem. So, what is the problem? That say you are in a start node, you have to traverse in node 1, say N1, say, then it is N2, then it is N3, then N4, then N5, then N6, then to end. There can be, of course, some intermediate vertices or some loop, kind of that. But the condition is you can only traverse from S to end using a Ham cycle. What is it? Like a Hamiltonian cycle. What do I mean by that? It means that from source to end, you can traverse. But the condition is intermediate vertices, you can only traverse exactly once. First condition. Second, you have to traverse all of them, all vertices once. That means you have to cover all the vertices, and it's a cycle. That means you have to come back to the original vertex. but only the source and the end vertex can be same. Except that all the vertices you have to cover, and after covering all the vertices, you have to come back to the original one. This is the criteria, and this kind of concept in mathematics or in graph theory is known as Hamiltonian cycle. And this path is known as Hamiltonian path. Now you might be asking the question like, why all of a sudden we are like really picking up this TSP? Like how it is really very relevant to the concept of quantum computing? You might be having this question. Let me answer that. So TSP is one kind of problem, like TSP, traveling salesman problem. Why it is very, 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 very relevant is because it is used in kind of shortest path problem. Now we can imagine the industry. Then it is used in kind of vehicle routing. It is also used in supply chain management. That means in logistics, in transport, and in any application or industry where you need anything from network, there is a huge application. And this is point number one. Point number two is this TSP, traveling salesman problem, is an NP hard problem. Now we will deep dive into what is NP, what is NP hard, what is NP hard altogether, and why it is a problem. Right? So we talked about it a little. Let me discuss. So first of all, let me give you the definition. So NP is, what is NP? Is it non-polynomial? NP, non-polynomial. Is it the case? Answer is a big no. NP does not stand for non-polynomial. If you know that, it's a wrong statement. What is the right one? NP stands for non-deterministic polynomial. What do I mean by that? It's a non-deterministic polynomial. Means if I have a deterministic machine, then I can solve it in non-polynomial time. Alternatively, alternatively, if I have a non-deterministic machine, focus, a non-deterministic machine, then I can solve the problem in polynomial time. Now, this is very fundamental to what we understand as P and in. So far, maybe we are understanding like P is polynomial and P is non-polynomial. It is wrong. What is correct? P is deterministic polynomial, meaning in a deterministic machine, it takes polynomial time to solve the problem. NP means it's a non-deterministic polynomial, meaning if you are able to manage a non-deterministic machine, then your setup is going to solve the problem in polynomial time. Now the question is what or how you can define a deterministic versus a non-deterministic machine. These are all very relevant for us to understand because where to apply quantum, how to apply quantum, if we have to understand that, we have to understand that the deterministic and the this particular logic. We have to understand. Because maybe in sorting, in searching, this is not something that we can apply for. You might say that Grover is one of the searching algorithm, but it literally proved an kind of a quadratic speedup. But generally, to show that, to prove that, it's very difficult in quantum setting. We can only do something in terms of a constant number of query. So in order to do that, we have to understand that what is the difference between deterministic and the non-deterministic machine. Simple word, if you remember automata, say you are in Q0, this is your initial state. From this state, on having an input A, you arrive to Q1. From Q1, say on having B, you arrive to Q2. Kind of this. Kind of. Say this is B. Let me take this as A. So this is an arbitrary DAG. But what most important here is to understand that how many states are here? Q0, Q1, Q2 and Q3. So these are all your states. Q0 is what? Your initial state. Q1, Q2, intermediate. Q3, final. So if you like notice here, from any state on having one particular input, you are actually reaching to one particular state. Is there any discrepancy? Is there any kind of like duality where from one state on having some input, you are reaching to multiple states? No. So this kind of deterministic logic is known as deterministic machine. On the contrary, let me consider here, say you are in an initial state Q0 on having A. You are reaching to Q1, Q2, Q3, Q4. So here Q0 is your final state. sorry, initial state. Q5 is your final state. Q1, Q2, Q3, Q4, all are the intermediate ones. And the transition function, like delta Q0 on A, will reach to Q1, Q2, Q3, Q4. So it has four possible options. Therefore, this is called non-determinism. And the machine is called non-deterministic Turing machine. So there are DTM, as you can see over here, and there are non-deterministic ones as well. Okay. Now the thing is, again, if we go back to the earlier discussion, why we are actually picking up this thing. So it is relevant for shortest path problem, relevant for vehicle routing problem, very relevant for the supply chain management, all the problems including the SCM. So the case is why this is very relevant. So right now we are into understanding without the theory in reality, like why TSP is important. For QC, say for example, I am standing in vertex number 1. I have a graph. That means a series of cities that I have to cover, where I will be starting from 1, then I have 2, then 3, then 4. Kind of. The edge connectivity doesn't matter because we will be considering that as if they are connected. Okay. So that means the function will look like, let me consider the function name is TSP. So I will be starting with this, where vertex 1 is my originating vertex, the first vertex. Then I have to cover all the remaining vertex. I have to cover. So that means there is a set where I have 2, 3, 4. Condition is I have to come back to vertex number 1 after all the traversal. So from this, initially, if you notice, it will be, so 1 is already covered. Then after 1, what is the next vertex that I can choose? Let me choose 2. So choose 2. So it is TSP 2, then 3, 4. Then it is, let me choose 3. So it is TSP 3, comma 2, 4. Or it can be like, let me choose 4. So it can be TSP 4, comma 2, 3. Now, similarly, it can be like, say again, choose 3. So the path is 1 to 2, 2 to 3. So it will be like TSP 3 comma 4. Similarly, it can be like when 4 is chosen, this similarly here. So it's like TSP 2 comma 4, then TSP 4 comma 2. And this one can be TSP 2 comma 3, this thing. So the theory is that, so next what we will cover is, we'll try to prove that how many total such sub problems. What do I mean by sub problems? Say this thing. Likewise, it's still not over yet. We will be choosing 4, then it will be TSP 4 comma epsilon. Likewise, but now our challenge is to prove mathematically that how many such subproblems are created for TSP 1, comma 2, 3, 4, where we have only 4 number of vertices. So the condition is, try to prove the number of unique subproblems. Unique means I have to do it only once to solve TSP with certain number of vertices. Let m equals to, say, n minus 1, that is excluding the source. Now say n total cities or vertices are to be covered, including the starting point. Therefore, the set of other, meaning like 1, 2, 3, 4, that kind of thing. So the set of other vertices are of size n minus 1. Now, each subproblem is defined as, say, TSP U mask, where Mask is a subset of 2, 3 till n, that is a set of all vertices excluding the starting vertex. Okay, and U also belongs to mask when when the last visited vertex we have to maintain the Hamiltonian cycle criteria. Now let's denote. See, remember what we are trying to all prove here is that why TSP is a good problem to consider, and it is a very relevant problem for quantum computing as well as for classical one to understand the complexity classes. Now, in order to do that, we are actually picking up or detailing the kind of the complexities that it has. And what is our primary target? Our primary target is to prove that the number of or how to relate the number of unique subproblems for TSP, right? So on that note, we are moving. I hope some of the basic things like you are having some understanding. We will be taking the questions, so then we can discuss a lot more. So let's denote. Let me like finish it first. Let's denote m equals to n minus 1. N is the total number of vertices. So this is excluding the source node. Now we want to connect or say count all pairs in the form of U and mask, where mask is basically a subset of 2, 3, likewise n, and mask is any subset of size k belonging to 1 and m. So therefore, for each subset of size k, there exists a mck number of such subsets for obvious reason. Okay, and for each of such subset, there are k number of choices for you. In that case, the total number of unique subproblems will be sigma k equals to 1 to m, then mck times k. Now mck is nothing but m factorial by k factorial into m minus k factorial. So this can be written as k or say it can be written as m factorial divided by k minus 1 factorial into m minus k factorial into k. Now this can be written as further m into m minus 1 factorial divided by k minus 1 factorial how to get that? By algebraic simplification. Now applying the identity over summation s equals to sigma k equal to 1 to m k into mck sigma k equal to 1 to m, then it's m into m minus 1 k minus 1. Now factoring out this m, we'll be getting s equals to m into sigma k equals to 1 to m minus 1 into k minus 1. Now if you change the index of the sum, say let j equals to k minus 1. So that means when k equals to 1, j equal to 0, and k equals to m means j equals to m minus 1. Or alternatively, it can be written as k minus 1 is equals to j. Then the summation s will look like m into this particular thing. Now, from this thing, if we apply binomial theorem, say now by applying binomial theorem, we know that for any integer n greater than equals to 0, x plus y whole to the power n is equals to k equal to 0 to n, then nck into x to the power n minus k into y to the power k. Now applying this theorem, applies this theorem with x equals to 1 and say y equals to also 1, we get here, let me put it, so it's 1 plus 1 power n times nck. Like simple calculation I'm doing. So this means that 2 to the power n is equals to nck, where k equals to 0 to n. So this means this also equates nc0 plus nc1 plus ncn. Meanwhile, it's nck as well. Okay. Now, setting m equals to n minus 1 or n equals to m minus 1, whatever you take, we are interested in summing m minus 1 j from j to m minus. Therefore, sigma m minus 1 j. Now this is equals to 2 to the power n minus 1. From where we are getting it? From all this theory. So this is from the earlier derivation. So since this represents the sum of all subsets of an m minus 1 element set. Therefore, S equals to m into 2 to the power m minus 1 is the fundamental formula. Now, initially it was so initially it was k equals to k 1 to m mck times k, which is equals to m into 2 to the power m minus 1. Now in TSP, with n number of total vertices, and we define that m is equals to n minus 1, number of unique subproblems are n minus 1 into 2 to the power n minus 1 minus 1. So this is the number of unique subproblems that you have in TSP. Now, therefore, the space complexity will be order of n minus 1 into 2 to the power n minus 2, which is nothing but order of n into 2 power n. And therefore, the time complexity is, or it is for all vertices, will be n into the space complexity. So this is n into 2 to the power n. So it's basically we go of n square 2 to the power. So this gives us an idea that why we are considering. Now see, remember, what is the complexity that we are getting? N square into 2 to the power n. What it is? Like time complexity. Now say your n is equal to 10. Then it is n equals to 15. Then it's say n equals to 100. So time complexity here will be 10 square into 2 to the power 10. Kind of. So here it is. So this is 10 like n square. So it's 15 square into 2 to the power 15. Kind of, kind of. So say n equals to 100. So it's basically, so you can imagine that if we keep on increase the size of the vertex, or in easy words, if we increase the size of the graph, if we include more number of cities which the traveling salesman has to cover, then it will actually make a huge impact on the complexity. And this kind of graph is exponential in nature. So this is why TSP or traveling salesman is called NP hard. So what are the few points that you should be remembering is here, that what is the space complexity? It's n minus 1 into, to be very precise, it's n minus 1 into to the power n minus 2. Then what is the complexity for space? It's n into 2 to the power n. Then what is the complexity for time? It is big O of n square into 2 power n. So this is the exact number of subproblems. This particular thing is space complexity, and this is time complexity. Okay, so just after that, let me show you one thing. Let me show you that if only 5 vertex is there, whether the number of unique subproblem is actually n minus 1 into that formula or not. Let me take one. Let me start with this CTSP1, then it's 2, 3, 4, 5. So subproblem from this will be TSP 2, 3, 4, 5. Then it's TSP 3, then 2, 4, 5. Then TSP 4, 2, 3, 5. Then TSP 5, then 2, 3, 4. Then from here it will be TSP 3, 4, 5. Then TSP 4, 3, 5. Then it's TSP 5, 3, 4. Now, similarly, this will be, what you have to remember here is what why we are doing it is because we want to understand that how many unique subproblems we have. So repetition we might be tackle separately, able to tackle it separately. But if it is any unique one, then we have to delegate some resource, some computing power to tackle them separately. So right now we are focusing on how unique all these problems are to each other. Okay, so this is 534. Now this one will be 245. Till now any repetition? I don't think so. TSP 425. Now this one will be, which one? This one will be, let me write here. So this will be TSP 235. This much. And this particular subproblem will be like TSP 234 324 423. Right? Now again, all these problems will be, all these ones will be, so this will now be TSP 4 then 5 and TSP 5 followed by 4. Similarly, like this kind of an expansion will happen for all the sub problems being called. Now TSP 4 5 or 5 4 say. In next step, it will be mapped to exactly one step where it will be TSP 5, comma epsilon. Why? Because right now, if 5 is taken, then in this set, there will be zero number of elements present. Similarly, so if we keep on doing that, there will be a certain cases where there will be little repetition. So what are the repeating element? Like TSP 5 epsilon, that might also come for TSP 3 5. TSP 4 epsilon might also come for TSP 2 4 or 3 4. So ignoring that, if we do that, ignoring that, the total number of the total number of subproblems that will come is belongs to n minus 1 into 2 power n minus 2, which is 5 minus 1 into 2 to the power 4 minus 2. Sorry, n is 5, so 5 minus 2. So this is 4 into 2 to the power 3. It is 4 into 8, 32. So this is the actual number of subproblems that we have for n equals to 5 number of cities. Okay. Now this entire thing is to prove that TSP is a hard problem. Let me take a pause here. Let me ask you if you have any question. Anyone? Any question you have?
Ma'am is asking questions that are related to the course regarding Canvas and other things you can ask later.
Yes.
Any doubts as of
Any kind of doubt you have, you can ask.
yeah, I think there is no doubt, ma'am. Maybe you can take a break for 5 minutes, ma'am, and then we can again continue. Meanwhile, participants, if you have any doubts, please drop the questions.
Yes, yes.
Yeah.
So we covered uh, epsilon is a blank point, blank when nothing is there. We almost like covered the first half. Next is the second half. I tried to show with some example, but you can try it out. You can check it like what are the unique subproblems if you are getting anything separately, because I'm unable to show you the entire solution space here. You can start with any 5 or 6 vertex and you can check it out. Okay. I hope there is no doubt. So what we actually is trying to cover. Now let me give you some brief idea about what we are doing. So basically the idea is, see, today we were about to cover the complexity classes. What were the classes? Like primarily we want to cover P, NP, NP hard and NP complex. But again, the question is, what is the relevance of knowing these things suddenly, all of a sudden, during the quantum computing lectures? So for that, we have to understand of one problem which is very kind of relevant to any of the domain, be it optimization, be it machine learning, be it any one of the fields where quantum can do some wonder. So that was your TSP, traveling salesman. What was the problem? It was to find the Ham cycle. What is Ham cycle? Hamiltonian cycle. What do we mean by that? It is we have to start with one vertex. We have to cover all the vertex. Then we have to come back to the original vertex. But the condition is that no vertex can be skipped and no vertex can be like visited multiple times. So it's only one chance we can visit one vertex exactly once, except the starting vertex, which we have to cover like twice, initial and the final. And then we explored, tried to explore that why TSP is a kind of problem that is being picked up or chosen by quantum. What was the reason? That is the number of unique subproblems. Unique subproblems was was exponential. That means there is no way we can reduce down or we can actually find out some strategic algorithm that can do some betterment with respect to the existing one for TSP, right? That is the number of unique subproblem. What do I mean if it is repetitive? What is the like logic behind it? If it is repetitive, that means that those kind of repetition we might be using some memoization technique. What is the technique? Memoization technique. What do I mean by that? Maybe there will be certain external array kind of that where a particular value will be directly stored so that we don't need to separately call for the functions. We can directly refer to the contiguous allocation and the values we can pick it up, right? So this is a technique which is used in dynamic programming. Why we are referring dynamic programming? Because this is so far the best, has no approximation, smartest, as the best algorithm, only handles unique problem or subproblem. So, because dynamic programming gives us these kind of features or benefits, we actually were using it. Now is the question, now that we all should be able to be on the same page that there are certain problems. So all the discussion that we have done is just to prove one thing, that there are certain kind of problems for which no matter how hard we try to find the unique subproblem, so that some of the repetitive tasks we can delegate on some earlier called functions. We cannot do that. If we have this understanding, then next we will jump to what is the definition of PNP we discussed a little at least. PNP we discussed. Traveling salesman problem we discussed. Now we will be discussing the NP hard and NP complete problem. Okay. Now, if you remember, I'll be taking the break maybe just after 10 minutes. Give me some time. Otherwise, the discussion will not have some like meaningful meaning. Okay. So, P and NP we discussed. So, Turing machine, we will start with a little bit of the theory. So, Turing machine is something that we had. What was Turing machine in easy words? Some kind of an abstract machine which we use to solve any problem. Simple words. It's a basic kind of a fundamental computing device or computing paradigm or mechanism that we use. Now the thing is, what is P? P was polynomial. What is the full form of P? It was deterministic polynomial. Meaning, if we have, like the definition of P is, let me write, if we have, this is not exactly the bookish definition, but this is exactly something that we should be understanding. So if we have some deterministic machine, what do I mean by this thing? Right now you should be knowing that, but just for your information, whatever machine we have, they are deterministic in nature by default. Okay, so we all have only whatever laptop, desktop, whatever we have, they believe or they work on the principles of deterministic logic. Okay, so if we have some deterministic machine, then a problem can be solved in polynomial time. What do I mean by that? Polynomial time means order of n to the power k, where n is the or base is the number of inputs, variables, k is some constant. Okay, so this is the fundamental definition. There can be certain alteration, but this is the fundamental one. So that means like complexity classes, order of say log n, order of n, order of root n, order of n square, n cube, all these complexity classes belong to P, right? Now, second is, then what is NP? NPR. Now consider, say we have some kind of DNA mapping machine or kind of a quantum machine with us. We already have that. And there is a problem that we want to actually solve it using that machine. Now, as I told you, quantum machine is by default non-deterministic machine. So that means NP will belong to those problems with those complexity classes where If we have some non-deterministic machine, we could solve it in polynomial time. Let me write it down. So if we have some polynomial machine, or say deterministic machine, then solving the problem, see, first I'm considering deterministic one. That is what we already have. So solving the problem will take non-deterministic time. Alternatively, second definition is if we have some non-deterministic machine, okay? So if we have some non-deterministic machine, then solving the same problem P, or let me write as A, will take polynomial time. So that means it will take like order of say k to the power n, where number of inputs is in exponent, constant is in base. So it can be like 2n, 3n, likewise. Okay. So these are two like kind of definitions for P and N. Okay. Okay. I want to pause here a little, kind of. Anyone has any doubt, any question, any part? Okay, you have any doubt? So far, what you should be understanding is one example which will clearly show you that what is the unique subproblem theory, why we like consider a hard problem. What is NP hard? I have not covered yet, but at least you have understood that there are certain problems which are very important to be considered in real world scenario as well, for which we might need the quantum theory or quantum complexity. Any doubt you have? Okay. What I want is to please take one example today itself if possible. Then take maybe 6 cities, try to match it, try to draw the entire search space. Don't skip anyone. Then just consider that how many unique one How many unique subproblem? Meaning if there are multiple like TSP 5 epsilon, say the 5 epsilon is there more than once or twice, then you have to consider it only once. Likewise, you consider that, then you take count of all the unique subproblems and just you check that despite of the brute force, we are unable to actually map the all the subproblems in a one space or one place. Okay, this is something that I want all of you to try. Just consider n equal to 6. So 1, then 2, 3, 4, 5, 6 will be the case. And those who are like very well equipped with algorithms, this must be something that you should be knowing and everything. But those who are not from computer science or algorithm part, I also like recommend all of you, please try it. Just check that why we need quantum. If anywhere we could do anything like the classical ones, we could be doing that. We all know that traveling salesman, supply chain routing, all these things, we all were kept on talking about it. But the reality is we should be understanding that the basic fundamental is there is no such unique or repeating sub problem which we could optimize if we use anything which is very strategic classical technique. So there is no such way which can be used over here. After that, we have learned what is P, what is NP, what is deterministic logic, what is non-deterministic logic. Only this. Is it clear to all of you? Is it clear to all of you? Very good. So on that note, let me like proceed further. So we covered P and NP. So we are left out with NP hard and NP cold. Now I will be using that beautiful story. So there is a class of computer science students. So say student 1, 2, 3, 4, 5, 6, 7, kind of. Okay. Now there is an IT student, say I1 or I dash. So I dash came into the computer science class and claiming what he is claiming? That I am at least as best as say your top or any one of you. Or alternatively, say he is telling that no student from CS can ever, ever beat me. What do I mean by that? That means IT student is at least better than any of the CS students. At least means even if you pick up the best student of computer science, he or she will be even less or at par with the IT student. If this is the true, like this is the case, if this is true, then IT student will be called an NP hard problem. What do I mean mathematically? Mathematically, it means remember the story of the CS and IT. Okay. Now, mathematically, it means for all problems P such that P belongs to NP. Right? If this is the case, then on that note, so right now I'm referring, say this is NP. Right now I'm referring all problems that belongs to the NP class, P. Okay? For all of them, such that if P is polynomial time reducible to P dash, then P dash is, or so alternatively, say for all P, P dash is polynomial time reducible to P. Then P dash will be called NP hard problem. Where this particular part means this is this particular symbols means as hard as. So P or P dash is as hard as any of the P problems. Then P dash is an NPR problem. So consider the example where say the IT student right now has came to the room and she's claiming like, okay, so I'm the best student, and whoever is your topper, I'm best than any one of your student. Or alternatively, what your best student can do, I can definitely do, but maybe the vice versa is not true. So that means I am at least as good as any of your CS student. Alternatively, I am at least as hard as any of the problems that you have in your NP category, where NP is equivalent to the computer science class. Is it clear now? Is it clear now? Let me ask. You got it? So this is not like something that we are doing right. Like today, whatever we are doing is not very much of a quantum, but it's very kind of a algorithm or classical thing. So just understand that NP hard is that problem which is at least as hard as any of the problems that already reside in NP. That is why we call it NP hard, as at least as hard as any of the problems in NP. Let me tell you. Okay, someone asked some question like what is the complexity of the NP hard problems? So you got one thing like what we were discussing, that the TSP1. So what was the complexity for TSP1? It was like the time complexity. Remember, whenever we refer to complexity, we primarily refer to time one. So the time complexity was n square into 2 to the power n and a big O of that. That means it belongs to this category or family. So this is an asymptotic notation known as big O notation. So which means that if it is bigger of n square n 2 to the power n, it implies that it belongs to the complexity class with certain constant into n square into 2 to the power n. So what is the complexity of NP hard? That means if it is hard, that means something will be there or has to be there in the exponent. This is the easiest rule by which you can identify that whether some problem is NP hard or not. Okay. So if any complexity is like this, say for example, like this, say 2 to the power n, 3 to the power n, 4 to the power n to the power n, or sorry, n to the power n, k to the power n, in factorial power n, kind of. Then these problems are called NP hard problems, where of course, traveling salesman or TSP is one of those. So TSP is NP hard means TSP is as hard as any of the problems that are in NP, right? Now, suppose there is an alternative scenario. Say, for example, you have a class of CS students, right? There is, say, S1, S2. Now, say there is one student, S8, and suddenly he stands up in class and claims that, hello, I am the new topper. So that means S8 is claiming I am as hard as any one of us, not you. Which means she also or he also belongs to the CS group, CS batch, computer science batch. Then they are kind of claiming, or she's kind of claiming that, okay, hello, I'm the new top. So what I can solve is what you all can solve, or what you all can solve, I can definitely solve. So at least that much of capability, intelligence I already have. In that case, this S8 problem will be called an NP complete problem. What were the definition? Say for all L dash, or say for all P dash, whatever it is, say L dash, where L dash belongs to NP. That is, it belongs to the computer science class, which is the NP class, non-deterministic polynomial. So for all L dash such that L dash belongs to NP, such that L dash will be reduced. All problems in L, okay, where L dash and L, like both are in NP, then that implies L dash is NP complete. What do I mean? This is for all symbol. So for all, L dash is generic one, such that L dash and L, like what I want to compare, with whom I want to compare. When both are in the same set, then L dash and L both under that condition that they belong to NP, such that L dash, that is any problem, like I said, if it is less than equals to P kind of L, where this is called polynomial time reduction. Okay, I forgot to mention it. This is not less than or less than equals to. This means polynomial time. P means polynomial time reduction. 2L, where L is all the like remaining or leftover problems in NP. If that is the case, then L dash will be called an NP complete problem. Okay, and that is why NP hard and NP complete are two primary kind of thing for us to consider for quantum, because a classical counterpart cannot do really any wonder with respect to these two complexity classes. Right? Again pausing. Anyone has any doubt? You can ask. So the fundamental kind of ground we covered. Was there any issue with my screen? Let me know, please. Or anyone has any doubt you want me to repeat anywhere? You can ask. These are very, very fundamental concepts of computer science itself. CS. Not directly, maybe directly related to the quantum, but these are very fundamental. Anyone has any doubt? Screen hang. No issue. I want two or like three more confirmation. Is it completely clear? If you recall, like in the very first class, we were referring this thing, that TSP, the combinatorial explosion, and all these things. So today we actually got to know the mathematical derivative of that. That why we cannot reduce it. Say for a particular problem, you all know that there can be multiple solutions. So maybe I solve a problem with order of n time, but you might be able to solve it in log n time. Then that means your algorithm is better than mine. But the consider is that like the problem is here is that what you have to consider is, if even if you apply the best algorithm, then also there is no solution. So first we have seen why TSP is an NP hard problem. Then we have seen the formal definitions of P, NP, NP complete, and NP hard. Clear? There is a problem P whose solution is not known, but if we prove that the solution cannot be lower than n to the power n. Absolutely. Absolutely. N to the power n, absolutely. Even the like Fibonacci and all, in factorial, it is actually n to the power n. One more thing, I will be talking about that. Like NP hard and NP complete, one thing we have understood that something belongs to NP, something does not belong. But what do I mean by that? That is the verifiability. If we can verify some problem that is in NP, then we will consider it for the NP complete. If we cannot even verify it, verify means, say I am telling you that, okay, like I'm giving you one key to my room. If you can verify it, or if you can, like, let me go back. If you can do that, like open my room with that key, that means it is working properly. If you are able to do that, then I will say that, okay, so that key is verifiable. But say there does not exist any such key, for example, then you will refer it as a non-verifiable problem. And NP hard problems are generally not verifiable because they are not also in NP. Okay. Okay. I have 5 more minutes. So I'll just start with a few basic little introduction. Say problem space. So what is a problem space? A computational problem. Let me write it down. Say it is a relation. What is a relation? Refer to set, relation, and mapping. Any word that you get, you have to go to deeper in order to understand that. I'll be asking question about what is a relation next class. So a computational problem is a relation P between a set of valid inputs I, that is a set of all valid inputs are referred as capital I, and a set of valid outputs, say capital O, such that for all in X belongs to I, the problem space P is like I or input space that will map to output space O such that X comma Y belong to P, where X belongs to I and Y belongs to. So this is a formal definition of a problem space, where the set of valid inputs will be mapped to the set of valid outputs on that condition that there will be some valid pair, input output pair, which will be mapped to the problem space. Right? Now, the set of all, let me write here, set of all valid inputs, I have told that it will be mapped to outputs. So this is your problem space. So this will be mapped to outputs. Now this output can be kind of two types. Feasible or feasible solution. That means your output can be feasible solution. Also, it can be infeasible solution. So feasible will actually satisfy all problem constraints. You have some certain predefined constraints, all of them will be satisfied. Infeasible one is that one that violates at least one, maybe more, maybe all, but at least one constraints. Okay. Next is there is another one type of category which is used for problems, which is correct solution. So what is feasible, what is infeasible? You got it? Now what is correct is a result output that exactly satisfies the problem specification for a given input. Meaning they will be feasible. Feasible means meeting all constraints. Then they will be accurate, like producing the correct answer. For example, what is the difference between feasible and correct? Say there is a competition where I want to give a prize ceremony kind of that kind of ceremony is there, and I'm telling like only the female candidates or whoever is the female topper they can participate, or please that candidate please come on the stage. Now infeasible means if a male candidate appears, it is not meeting that constraint. Or say I'm telling that okay, only the third year female topper. If second year, fourth year, first year comes, then that means they are not meeting that constraint or criteria. So they are infeasible solution. What is feasible solution? If a third year female candidate turns around, if she turns out, right? Now when that female candidate from third year will be a correct one, only when if she is a topper as well. That means she actually is maintaining all the constraints as well as she is the like required candidate who should come up. If both the conditions hold true, then that feasible solutions become a correct solution. So that means feasible is a kind of superset of the correct solutions. Right? So that is the story. We can end here. Now, whoever takes the next class, what you should be like practicing a little bit about is CFG, uh, context-free grammar. Then it's like Chomsky classification of grammars, which primarily you can find it out in any of the like automata theory book. So this is basically the type 0, 1, 2, 3 grammar. Then the next is a little bit about the if you want, or what we can cover next is decidable, undecidable. And once we have the understanding of Chomsky one, we can also go to recursive. Then it's RE, recursively enumerable, and NRE, non-recursively enumerable language. After having all these details, we can enter into the quantum complexity classes. Everything needs to be backed up by the why, then what. So for that, we have to understand this part, and whatever we have like covered in today's class plus this one, then we can enter into quantum complexity classes. Okay. I think we can pause here.
Oh, camera. Yes, ma'am. If there are any doubts, we can ask. Otherwise, participants, if you have any doubts, you can ask. Tomorrow we'll start with quantum cryptography by Ms. Janani. So if there are no further doubts, we'll conclude here. Yeah. Thank you so much, Nivedita ma'am. Last moment, you have once again helped us, and without much reluctance, you've taken the lecture. And thank you so much once again. And we will continue the sessions tomorrow at 3 o'clock, and we will meet tomorrow. Ma'am, there's one question.
Yes. It's like finding a passkey by brute force. It might take exponential time. If we can verify it, that means it is in NP. So it will be then NP complete, not NP hard. So you can consider it like NP hard is even harder, kind of. So meaning a problem, it does not have a solution which you can even verify. Okay. So that kind of problem is NP complete problem. If you can verify. If you cannot, then it is a NP hard. Okay. Yes. Verifiable means it is in NP. Then if it is that hard, like at least all the problems that are in NP, then it is a NP complete problem. Even if you cannot verify it, only it is as hard as any of the problems in NP, then it is NP hard. Okay. Any other problem? Any other like doubt you have?
Yeah.
The base book for the complexity classes will be Foreman. Follow that one. It's kind of a god for us who like want some detailed understanding of the theoretical computer science. Please follow Foreman. You can also follow Shani or with Shani, but Corman will be the best book. Corman.
CORMEN. Type.
Yeah, I might be like wrong with
Book
the
is an
spelling.
algorithm.
Just check it. Yeah,
Yeah. Corman. Yes.
yeah.
Yeah,
These are
madam.
like a lot of mathematical things are there. A lot of like detailed understanding you need to do, reducibility. A lot of things are there. But today I just tried to like cover it in a way so that at least the fundamental will be clear to all of you. You have that thing in your mind. That's it. That's Shahani. That book by Shahani. Let me write it down.
SAHNI. Sahani.
Uh,
Horowitz.
yeah.
Sahani.
Harviz Shahani. Yeah. Very good one. Shahani is actually something if you want some detailed mathematical ones or kind of that. And Corman is like everything. If you want to know anything and everything about algorithms, your data structure, you can actually refer Corman. I think you can understand like today's class was nothing from quantum. It was fully classical. But that's why I'm referring. These are only for the algorithms and the complexity classes.
Yeah, the course is also foundations of quantum. So basically, we are trying to build the base actually. The base is built and then you can actually take it forward, right? So that's the basic idea.
Yes, so today's class you will be actually getting the benefits when we'll enter into quantum machine learning and all. that why for the supply chain routing and all these things. So, like understanding the why is very important. So, we'll be getting the fundamentals from like this thing.
Right, ma'am. Thank you so much, ma'am.
Dr. Shabakar, sir, I want to say something.
Yes, sir. Please go ahead.
First of all, I thank Dr. Nivedita Dev Madam for a wonderful session. And sir, on behalf of APSCHE and all our participants, I would like to congratulate you for defending three of your students, Anil Prajapati, Aditi Sheta, and Anubha Jain. Hearty congratulations, sir. It's really a epoch-making day for you. That simultaneously, you are producing three scholars from you, and they will be awarded PhD very soon. I think it is already awarded.
Yes, sir. Yes, sir. Actually,
Okay.
October
Okay.
1st and 3rd, we had holidays actually, and I could
Okay.
complete that work. That was
And
the
I could
advantage.
also read, with your permission, privacy aware defense mechanisms for RPL routing attacks in IoT. It is for Anil Prajapati. And also disruptive event detection using online social media for Aditi Sita. And enhancing privacy and threshold schemes for Bitcoin using Taproot. It is for Anubha Jain. Very nice to read all this. And on behalf of APSCHE, I would like to congratulate all your students also, sir. Thank you.
Thank you. Thank you, sir. Thank you so
Thank
much.
you.
Yeah. Yeah. Thank you. And they are not on quantum actually, but slowly the quantum PhDs will start now. Yes. Two students are sitting here, Diksha Java and Ritya Sharma. Both of them are working on quantum. Right. Hopefully,
Great.
sometime. So, yes, sir. Thank you, sir. Thank you very much. Yeah, thank you, ma'am. And thank you, participants. A good number is joining. We are very happy that you are taking things very seriously, 600 plus every day. And it's a good effort from your side also. We will meet tomorrow at 3 o'clock. Right. Thank you.
Thank you, everyone. Thank you, sir.
Thank you, ma'am.